Okay, in this video we're going to be looking at calculating elements on map projections. But before we start into the actual calculations, we need to have a little bit of a look at things. So here we are, we've got set up our typical projection with a north and east there, and we can see our projection where we've got the latitude and longitude of the projection origin and the central meridian indicated up and down here. Now, and these are our various meridians or projected meridians, and here we have the projected meridian going through a point A. Now at the point A we have grid north, which is parallel to the central meridian of the projection, but also at point A we will have true north, which will be slightly different from grid north, and at the angle between grid north and true north is what we know as the convergence. So there we are, showing how the convergence is the angle between grid north and true north, which is the obviously true north being sort of at tangent to the meridian at the point through A. Usually our meridional circuits and such are designed so that this convergence is not too great. Okay, moving right along now, we're taking a closer look at the point A, and from the point A we are observing to a point B, observing a bearing. Now, the first thing to note, of course, is that we have what's known the straight line between A and B, and this is our this would be our grid. This would be what would be represented as our plane distance or our grid distance, and our grid bearing, and these are what is shown in our projection. However, as we noted earlier, we have the true north through the point A and grid north with our convergence, and then we also have, when we're observing at A to B, we would actually be observing along this green line here, which is a tangent to the projected geodesic, which is the chord or the arc between A and B. So this is what we would actually be observing. So if we have a little bit of a look at this, here we've got our convergence here, and here we've got our what we call our ellipsoid bearing here, which is round through here. Our grid bearing would be round through here, and then we've got what we call our azimuth, which is this in here. But also in here we have our arc to chord correction, which is this little thing in here. So when we're observing a bearing from A to B, we actually observe along here, but we need to calculate the arc to chord correction so that we can change our observed elliptical bearing to a grid bearing. Further to that, we also, of course, we measure the elliptical distance, which is what we actually measure, but we actually have to apply a correction to correct it to make it into a grid distance. So and this arc to chord correction here generally doesn't come into play except on very long lines, and we're going to do a calculation on a line that's about 50 kilometers long, and we get a 1 second arc to chord correction. So it's only comes into play when we're observing very long lines, and generally in our most of the stuff we do in observing these days, observing and measuring distances, is over short lines. So these are diagrams to sort of explain what we're dealing with here. So let's have a look at a few formula and a workflow. So the first thing we need to do is we obviously have the coordinates of our point that we're going to start with A, and but they are of course in terms of the projection, so we need to find out those coordinates in terms of the true origin, or in other words we've got to just subtract the false origin values from it. So E dash A equals E of A minus E0, which is the easting of the false origin, and similarly in the northing of the false origin. And then we're going to work out the approximate coordinates of B. So all we need to do there is the easting of B is equal to the easting of A plus the elliptical distance that we measure times the sine of the elliptical bearing. And similarly, that's in the eastings, and in the northings, same thing goes. So we just need to do that. Now for the arc to chord correction, A to B, we've got a little beta minus alpha typically is how the arc to chord correction is shown, and here's the formula for that. Now note that this formula, the values are given in radians. So what we have to do is, once we've got the radians, is to multiply by 180 over pi times 60, which gives us approximately 264.8062. We multiply our answer to that, and that will give us the answer in arc seconds. So that needs to be the, and then we work out our grid bearing from A to B. And here it is. Here it's the grid bearing equals the ellipsoidal bearing plus the arc to chord correction. Now we also then move ahead and move out on with the line scale factor A to B, which we can determine as a scale factor, or by going through a little process here we can convert it into parts per million. So the grid distance from A to B equals the scale factor times the ellipsoidal distance, which is shown here. And then of course once we have the grid bearing and the grid distance, we can work out the coordinates of B using this same formula as we did earlier to work out the approximate coordinates, and there we go. Right, now here's an example we're going to use. What I've done here is using software, I've calculated the vector from trig Taupri to Te Aroha. These are two trigs that were used as part of the first major triangulation of New Zealand, so I was quite sure that they were quite a reasonable distance apart and that they had quite good coordinate values. Now using survey software, of course, because we've got good coordinates of each end, we can do this. However, if we're determining a new line, that's a bit of a different story. So just in calculating between these two, I managed to determine that there was a plane bearing of 81, 32, 32.79, and the arc to chord correction was minus 0.01 seconds. So this meant that the ellipsoidal bearing would be 81 degrees 32 33.79. So we had to subtract it, but because we were subtracting a negative, it became positive. The plane distance came out as 49,723.398. The ellipsoidal distance, which was given by the software, as 49725.904. So what the objective is to calculate the chords of Te Aroha just using the ellipsoidal bearing and distance from Taupri, so as though that we had just observed those. That was our bearing and that was our distance that we'd observed, and so we're going to reduce those using the formulas and the information provided earlier. So we need to find out a little bit of information about our projection. So these particular coordinates are in the Mount Eden 2000 circuit, which is a transverse Mercator projection. There's the latitude of the origin, longitude of the origin, false northing 800,000, 400,000, and the central meridian scale factor of 0.9999. So the coordinates on the true origin of the trig Taupri, where we're starting from, are calculated out here. Just need to remember that the Earth's radius for this calculation is 6374000 meters. That's our Earth's radius there that we use quite significantly in our. Alright, first up what we're going to do is to calculate the approximate coordinates going forward of the forward station. So we put in our elliptical bearing and elliptical distance, and we run that out just using a straight rectangular to polar reduction, or polar to rectangular in this case, and that enables us to calculate our coordinates of the forward mark. Then using those, we're going to now work out the arced chord correction, and we feed that information into the calculation shown. Note the 264.806 we're multiplying at the end to convert the radians to arc seconds. So I've filled in all the values there, and surprise surprise, we get the answer of 1 second minus 1 second. Now the grid bearing equals the ellipsoidal bearing plus, and it's a negative 1 second, so that gives us our bearing of 81 degrees 32.79. So there we have it, fairly simple sort of calculation of the grid bearing. Remembering that this would, if we had just observed this, it's so much easier because we have a coordinate at the other end, but that's just there for the purposes of checking our calculations to making sure that we're doing it right. Now, right, for the next thing to do is to compute the grid distance, and using the formula shown here, and the easting values mostly, we calculate. Remember, this is the easting at Taupri, this is the easting at Taupri, this is the easting at Te Aroha, and we're all familiar with the radius and our K0 values. So they've all been filled in there and run out, and we get this value here for the K, or the line scale factor as it's sometimes known as, 0.999949586. Now we can convert that to parts per million by simply subtracting this value from 1 and multiplying by a million, and that's 50.4139 ppm parts per million. Now the grid distance very easily worked out, but this is from Taupri to Te Aroha, is our elliptical distance multiplied by the scale factor, which gives us 49723.397. Now let's just, as a check, using those values, compute the final chords of TA from those values, and again 81, 32, 32.79, 49, 723.397, as I've said earlier, and we run those out as we did when we calculated the approximate coordinates, and these are the values that we come up with. And I just checking back here, we can see that the actual values that we started with for Te Aroha were 726.976.890, so there's a millimetre there, and 486.454.043, and we've got a millimetre there. So I think that's a pretty good sort of confirmation that we've got that calculation done correctly, and that shows that we know what we're doing. Now you may want, if you were to do this on another projection, say for instance New Zealand map grid or something like that, you would have to go right back to the start and recalculate the bearing and distance between the two transformed coordinates. You couldn't use this bearing and distance, it would be different. So if you wanted to show that you're able to do this on another projection, say for instance the New Zealand map grid, then you would need to convert the Mount Eden 2000 coordinates for each point to New Zealand map grid, and then using survey software calculate out a bearing and distance between those coordinates, and then work through the calculation with that. So there you are. That's how we deal with these, calculating these sort of parameters and what have you on various projections, remembering of course that this was a 50 kilometre line and it made a difference of 1 second. That can very much depend on the projection, and and that type of thing. But generally these are calculations that need to be considered when we're measuring and observing very long lines.